In our last lecture, we have discussed displacement analysis through examples using only graphical method. Today, we continue our discussion on displacement analysis, but through the other method, namely the analytical method. Now, when do we use analytical method and when do we use graphical method? As we see, the graphical method, there is an inherent limitation on the accuracy because of the scale of the figure and your drawing inaccuracies. So, analytical method is preferred when we want higher accuracy, or if the displacement analysis has to be carried on for a very large number of configurations, and the graphical method, the picture becomes really cumbersome. And the other advantage of this analytical method, that it is amenable to computer programming. Now, before we get into the details of the analytical method and solve examples showing the power of the analytical method, let us go through the basic methodologies that is followed in this analytical method. As we know, all mechanism consist of closed kinematic loops. So, first task is to identify all the independent closed loops that exist in the mechanism. Next, we express all the kinematic dimensions like link lengths, offsets, and also the slider displacement by planar vectors. Then the third step is to express for every closed loop what we call a loop closure equation in terms of these vectors that we have just now said. Now, each such vector in a 2D, that is in the planar linkages, is equivalent to two scalar equations. That means, if a vector equation is there, that is equivalent to two scalar equations, and two unknown quantities can be solved. Now, once all these vector equations are generated using all the independent closed loops, one has to solve these equations to determine the unknown quantities that is relevant to a particular problem. And one has to remember that in general these equations are nonlinear algebraic equations and can be solved only numerically. However, in such simpler cases, just like a 4R mechanism, or if there is a 4-link closed loop, then we can show that these nonlinear algebraic equations reduces to quadratic equations and can be solved analytically. So, we start with a example that is the simplest one, that suppose we are given all the link lengths of a 4R linkage, then determine the orientation of the coupler and the output link when the orientation of the input link is prescribed. So, this is a problem of displacement analysis. We are given all the kinematic dimensions and the position of the input link, and the task is to determine the position of all other moving links for that particular configuration. This diagram shows a 4R linkage O2, A, B, O4. As we see, the fixed link O4, O2 suppose has a length L1, and O2A, the second link, has a link length L2, AB, the coupler, has a link length L3, and O4B is the fourth link with link length L4. The problem is, suppose these 4 link lengths are prescribed and the orientation of one of the links, say input link, that is O2A, is given by this angle theta 2. Our objective is to determine the orientation of the coupler and the fourth link, that is O4B. To do this, first we set up a Cartesian coordinate system x y with O2 as the origin. The first task, as I said, we have identified a closed loop, namely O2, A, B, O4, O2. Then the link lengths L1, L2, L3, L4 are represented by 4 vectors, namely L1, L2 L3 and L4. These vectors are shown by these arrows in this diagram. Now, the angle that these vectors make with the x axis we are using as the reference angle for to determine the orientation of these vectors, that is theta 2, theta 3 and theta 4. Theta 1, that is the angle made by O4 O2, that is the vector L1 with x axis, is obviously 0. We can express this loop closure equation very simply as L1 plus L2, these are all vectors, plus L3 minus L4 is equal to 0. This is what we say as the loop closure equation expressed in terms of link vectors. To analyze this equation, we write L2 vector in terms of complex exponential notation, that is L2 e to the power I theta 2. Same for L3 vector as L3 e to the power I theta 3 and L4 vector as L4 e to the power I theta 4. Since theta 1 is 0, the vector L1 is simply link length L1 into e to the power I 0, which is 1. So, the loop closure equation, let us substitute these complex exponential notation. So, we get L1 plus L2 e to the power I theta 2 plus L3 e to the power I theta 3 minus L4 e to the power I theta 4 is equal to 0. We know e to the power I theta is cos theta plus I sin theta. So, first we substitute for all these angles e to the power I theta 2, I theta 3 and so on in terms of cosine and sine, and equate the real and imaginary parts of this equation, complex equation separately to 0. This is nothing but really adding the x components to 0 and adding the y component to 0, because it is a closed loop. As a result, we get L1 plus L2 cosine theta 2 plus L3 cosine theta 3 minus L4 cosine theta 4 is 0, and adding the imaginary parts, that in the sine components, we get L2 sin theta 2 plus L3 sin theta 3 minus L4 sin theta 4 is equal to 0. Thus, a vector equation, because it is a all these vectors are two dimensional vectors, from one vector equation we get two scalar equations like equation 1 and equation 2. Each vector equation is equivalent to two scalar equation if the vectors are two dimensional. Now, from these two equations we can eliminate one of the unknowns, say either theta 4 to solve for theta 3, or we can eliminate theta 3 to solve for the unknown theta 4 if L1, L2, L3, L4, that is the link lengths are given and the input angle theta 2 is prescribed. Now, let me carry out this algebra to determine say theta 4. To determine theta 4, we write L3 sin theta 3 cos theta 3, sorry. Okay, I can write this first, sin theta 3 is L4 sin theta 4 minus L2 sin theta 2, and from the first equation we write L3 cosine theta 3 equal to L4 cosine theta 4 minus L1 plus L2 cosine theta 2. From these two equations, if we square and add up, obviously from the left hand side I get only L3 squared. So, I get square and add these two equations, we get L3 squared is equal to L4 squared plus L1 squared plus L2 squared minus twice L2 L4 sin theta 4 sin theta 2 minus twice L4 cosine theta 4 into L1 plus L2 cosine theta 2 minus twice L1 L2 cosine theta 2. Let me carry out this algebra a little further, and now onwards I will write capital C for cos and capital S for sin for brevity. We can get L3 squared is equal to L1 squared plus L2 squared plus L4 squared plus twice L1 L2 cosine theta 2 minus twice L2 L4 sin theta 4 sin theta 2 minus twice L1 plus L2 cosine theta 2 into cosine theta 4. If we divide now both sides of this equation by twice L2 L4, here I have missed out one L4. So, let me write out here. Now, divide all the terms of this equation by twice L2 L4, and as a result we will get a simple equation A sin theta 4 plus B cosine theta 4 is equal to C, where A is given by sin theta 2, that is coming from this term. From this term, B will get L1 by L2 plus cosine theta 2, and C L1 squared plus L2 squared minus L3 squared plus L4 squared divided by twice L2 L4 plus L1 by L4 cosine theta 2. So, we see if theta 2 and all the link lengths are given, these quantities, namely A, B and C, are completely known, and the only unknown is this theta 4, which has to be solved. But as we see, this is not a linear equation in theta 4, because it involves sine and cosine. to solve this angle theta 4 unambiguously, that is, we need not judge the quadrant in after we get the value in what quadrant the angle theta 4 lies, it is always better to replace sine and cosine by the tan of the corresponding half angles. That means, we write sin theta 4 as twice tan of theta 4 by 2 divided by 1 plus tan squared theta 4 by 2, and cosine theta 4 we write 1 minus tan squared theta 4 by 2 divided by 1 plus tan squared theta 4 by 2. Substituting this in that a sin theta 4 plus b cos theta 4 equal to c equation, we get a quadratic equation in tan theta 4 by 2 as follows. B plus c tan squared theta 4 by 2 minus 2a tan theta 4 by 2 plus c minus b equal to 0. So, finally, we get this quadratic equation in tan theta 4 by 2, where a, b and c are all known quantities in terms of the link lengths and the given input angle theta 2. Now, this is where tan theta 4 by 2 is useful. I get a quadratic equation and I get two roots, namely tan theta 4 by 2 is equal to a plus minus square root of a square plus b square minus c squared divided by b plus c. So, you get two roots for tan theta 4 by 2 and the right hand side may come out to be positive or negative. Of course, it can never be imaginary once the kinematic diagram is okay, that is a 4R linkage has been made, a closed loop has been obtained, a, b, c will be of such values that this square root can never be of a negative quantity. So, we may get 2 positive, 2 negative or maybe 1 positive and 1 negative. Now, tan theta 4 by 2, as we know, if theta 4 is between 0 and 180 degree, then theta 4 by 2 will be between 0 to 90 degree and tan will be positive. And if theta 4 is more than 180 degree, then theta 4 by 2 will be more than 90 degree and tan theta 4 will be negative. So, depending on the positive and negative values of tan theta 4 by 2, I can easily determine uniquely the value of theta 4. Suppose we are also interested in finding the orientation of the coupler, that is the angle theta 3. Then, so if we look at these two equations, we see L3 and L4 are appearing exactly the same way, only L3 is appearing on the left hand side and L4 is appearing on the right hand side. It is even more clear if we look at these equations number 1 and 2. You can see L3 and L4 are appearing exactly similar way, only thing plus and minus. So, when we have eliminated theta 3 and obtained theta 4, following exactly the same procedure, I can eliminate theta 4 and obtain theta 3. We have to remember that L4 has to be replaced by minus L3, rest of the solutions remain as it is. So, following is exactly a similar method to eliminate theta 4, we can get theta 3, a very similar equation like tan theta 3 by 2 will be equal to a plus minus square root of a square plus b squared minus c prime squared divided by b plus c prime. As we might have remembered that the quantities a and b did not involve L4 or L3. A was sin theta 2 and b was cosine theta 2 plus L1 by L2. However, the quantity c involved L3 and L4. That is why we have to replace c by c prime, and expression of c prime also will be very similar to c, and we have to interchange L4 by minus L3 and vice versa. That is, we will get c prime as L1 squared plus L2 squared minus L3 squared plus L4 squared divided by twice L2 L3 plus L1 by L4 cosine theta 2. The thing to note that for the same set of given lengths and the same value of theta 2, we have obtained two values of theta 4 and two values of theta 3. This is nothing surprising if we remember that even by graphical method we would have got two solutions for the given link lengths and the input angle. This aspect is very clear if we draw the same problem, if we solve the same problem by graphical methods. Suppose we are given L1, that the length O4 O2, the link length L2, that is O2A, and the angle theta 2. All these are prescribed. So, we reach from O4 O2 to A. The link lengths L3 and L4 are given. So, I can draw a circular arc with A as center and L3 as radius, and we get this circle. So, the point B must lie on this circle. Similarly, if I draw a circular arc with O4 as center and L4 as radius, we get another circle, that is this circle. So, the B must lie on this circle if I come from O4, and B must lie on this circle if I come from A. These two circles, as I said, in general will intersect at 2 points, namely here B1 and B2. So, we get two different configurations for the same values of link lengths and theta 2. One is O4 O2 A B1 and the other is O4 O2 A B2. Two configurations are shown distinctly, one by the firm lines and the other by the dashed lines. Now, we have got two values of theta 3 and theta 4, which are indicated in this diagram as well. For the firm line, that is when the diagram is above the line O4 O2, this is theta 3 1 and this is theta 3 2. Corresponding to theta 3 1, I have theta 4 1, and corresponding to theta 3 2, I have theta 4 2. Now that we have seen how to obtain various values of theta 4 as theta 2 changes, now we will show you the typical variations of theta 4 versus theta 2 for various types of 4 bar linkages. For example, here we see what we call a crank rocker linkage. That means, it is obviously a Grashofian linkage and a crank rocker, and theta 2 goes from 0 to 2 pi. And theta 4, because theta 4 is the rocker angle, it only goes from a minimum value to a maximum value. And there are two branches, one is here and the other is there. Because it is a rocker, again it rocks either from this minimum value to that maximum value or from this minimum value to that maximum value. As we said earlier that Grashofian crank rocker has two distinct branches, two distinct modes of assembly, that is why these two curves never cross each other. If you are starting on one of the curves, you will always remain there, either on this curve or on this curve. You can never go from one curve to the other, because each curve corresponds to a particular mode of assembly. Suppose we have a Grashofian double crank. This is the typical theta 4 versus theta 2 characteristics of a double crank. As you see, theta 2 goes from 0 to 2 pi and theta 4 also goes from 0 to 2 pi, because both the input and the output lengths are capable of making complete rotations. But because it is a Grashofian linkage, there are two distinct modes of assembly as represented by this firm line, and the other mode of assembly is by this curved line, and these two curves can never intersect, that is, each curve corresponds to a particular mode of assembly. If we have a Grashofian double rocker, then again we have two loops, one as we see here and the other there. Because this is double rocker, neither theta 2 nor theta 4 can make complete rotation. So, they are limited between two extreme values. For example, for theta 2 from here to there, and from theta 4 it is here to there. Again, there are two distinct loops for two different modes of assembly. Either you are following this curve or you are following this curve. You can never pass on from one mode of assembly to the other. Now, let us see what happens in a non-Grashof linkage. If it is a non-Grashof linkage, then it has to be a double rocker, and theta 4 versus theta 2 plot for a non-Grashof double rocker looks like this. Here again, neither theta 2 nor theta 4 can make complete rotation. Theta 2 is restricted within this region, theta 4 is restricted within this region. But there is only one curve, because there is only one mode of assembly, and as you see, this curve shows that the mirror image configuration can be taken up by the same assembly. You can generate the entire curve by one mode of assembly. Just now we have seen how to do the displacement analysis by analytical method for a very simple mechanism, that is a 4R linkage, which consists of only a single loop. Now, let me show how we can use the kinematic analysis, the same analytical method, for a little more complicated mechanism like the slotted lever quick return mechanism, which we did last time by graphical method. This figure shows the kinematic diagram of the slotted lever quick return mechanism. It has 6 links, namely the fixed link 1, input link 2, which is the line O to A, then this block which is link 3, and the slotted lever link 4, the tool holder link 6, and the link connecting the slotted lever with the tool holder, that is link number 5. So, there are 6 links with 2 sliding pairs, one between 1 and 6 and the other between 3 and 4. So, to do the kinematic analysis of such a mechanism by analytical method, let us first identify that there are more than one closed loop. We draw all the link lengths by the corresponding vectors, like L2 is the vector which represents the link second link O2A, L1 is the other vector which represents the fixed link O2O4, and O4A, that is the slider displacement, we use another vector, namely S4. Similarly, the slider displacement we represent by another vector S6, and O4B is the other link 4, that is the link vector. L5 is another vector representing the link BC, that is the fifth link. So, here what we see that there are link length vectors like L 1, L 2, L 5, L 4 and L 6, that is the distance of the slider movement from the point O 2. So, these 5 L 1, L 2, L 4 and L 6, these 5 link length vectors are constant, they are not changing with time. Whereas, there are 2 other vectors, namely S 4 denoting the distance O 4 A is changing with time. Same is true for S 6, which represents the movement of the cutting tool. Here it is DC represented by the vector S 6. And all these vectors, the orientation of these vectors I represent by angle theta measured from this horizontal line in the anti-clockwise direction. So, we can have one closed loop O 2 A O 4 O 2, which means L 2 is equal to L 1 plus S 4. This is one loop closure equation in terms of link length vector and sliding displacement vector. I can have another closed loop, namely O 2 A B C D O 2. There is an independent loop, and corresponding to this independent loop I can write L 2 plus L 4 plus L 5 is equal to L 6 plus S 6. So, this is a second vector equation. So, we have 2 vector equations, which as I said earlier are equivalent to 4 scalar equations, that is equating the real and imaginary parts or x and y components, however you said it. From these 2 vector equations I get 4 scalar equations. So, I can solve for 4 unknowns. Now, let us see in this problem what are the unknowns. What is prescribed to us are all the link length vectors, that is L 1, L 2, L 4, L 5 and L 6, and the input angle theta 2, that is the angle that this link 2 makes with a reference line, that is the x axis. So, these are given and we have to find out the orientation of all other links and also the slider displacement, that is S 4 and S 6. So, the number of unknowns are theta 4, that is the orientation of link 4, that is the line O 4 B, theta 5, that is the orientation of the fifth link, that is B C, that is this angle theta 5, this angle as I said earlier is theta 4, and also this distance O 4 A, that is S 4, and the distance D C, that is S 6. So, these are the 4 scalar unknowns which can be solved using these 2 vector equations. That is how we carry out the kinematic analysis through analytical methods. Later on, we will solve some more different types of problems and show the use of this loop closure equation and the vector representations of link lengths. As a second example of this kinematic analysis through the link vectors, let us look at the model of this mechanism, which is a copying mechanism or plagiograph. What we see here, that this is a 5 link mechanism, the fixed link, and there are 4 moving links 2, 3, 4 and 5. And the dimensions of these links are such that this forms a parallelogram. This link length is equal to this link length is equal to this. And these 2 triangles are similar triangles, that is this angle is same as this angle and this angle is also same as this angle. Now, in this mechanism we will show later that whatever is the movement of this point, that is reproduced by this point. Only thing, there will be a change in the scale and the orientation. For example, if I move this mechanism such that this point follows this vertical line of this letter L, then this point is also following a straight line, and as we go around this letter L, this point will also draw a L to a bigger scale and a different orientation. The question is that if we are given all the link lengths and the angle of these two similar triangles, then can we find out what is the scale of the reproduction, that is what is the change in the ratio of the size of these two L's, and what is the angle of these two L's, what is the angle, that is the change in the orientation of this letter L to this drawn L. As we see here, the L is okay, and here it has been rotated by 90° almost in the clockwise direction. The question is, for this given mechanism, that is the link lengths are given and the angles are given, can we find out that what is the ratio of these two figures and the orientation between these two figures? That will be our second example. This diagram shows the kinematic diagram of the model of the mechanism which we have just now seen, that is that copying mechanism or plagiograph. As we see in this mechanism, we have 5 links. One is the fixed link, O2A is the second link, O2C is the third link, BC is the fourth link, and AB is the fifth link. So, it is a 5 link mechanism. So, let us say N is equal to 5. Now, let me count the number of hinges J. We see there are 3 simple hinges at A, B and C. So, J1 is 3. At O2, 3 links are connected, namely the fixed link 1 and link number 2 and 3. Since 3 links are connected at O2, this is a second order hinge, that is of the type of J2. So, J2 is 1. So, we get J equal to 4. So, if we calculate the degree of freedom F, which we have seen 3 times n minus 1 minus 2j. Sorry, this is, I made a mistake here, J2 is 1, but J2 is 2 J2. So, this should be counted as 2 into 1, that is 2, and J is 5. So, F is 3 into 4 minus 2 into 5, which is 2. Thus, we have a 2 degree freedom mechanism, and this point D of this link can be taken anywhere arbitrarily on this plane, because it has 2 degrees of freedom. It can take any x value and any y value. So, this point D can draw any figure. Now, let us consider this O2A B C to be a parallelogram, that is link length O2A is same as BC and link length AB is same as O2C. Thus, O2ABC is a parallelogram. Not only that, the triangle ABD and the triangle BCE are similar, as indicated that this angle alpha is same as this angle alpha and this angle beta is same as this angle beta. So, these two triangles, namely BCE and ABD, are similar. Now, we can show that the movement of the point D and the point E will be very similar. That means, the movement of the point D will be copied by the movement of the point E. Accordingly, E will also draw a similar figure as D. The only change will be the size and orientation of the figure. For example, here if the point D writes this letter H, then E will write this letter H, but the height of this leg of the H is capital L and here it is small l. Similarly, this H is the normal way, that is vertical, and this H is almost horizontal, that it has been rotated through an angle sigma. Our task is, given the link lengths, let us find what is the scale of the reproduction, that is what is the value of L by L, and what is this change in orientation, that is what is the angle sigma once we are given the link completely, that is the link lengths and the angles alpha and beta. To do this, we use the link lengths as vectors. Suppose the position of the point D, that is represented by this vector x, and the position of the point E, that is represented by the vector y. What we can see, we can easily write vector x is vector O2A plus vector AD. Similarly, vector y we can write as vector O2E, which is vector O2C plus CE. So, we can write O2C plus CE. Now, we see that the vector O2C is same as the vector AB, because AB and O2C are parallel and are of equal length. So, we write O2C is same as the vector AB, and the vector CE, as I see, is a vector which is rotated from the vector CB through an angle alpha in the counterclockwise sense and magnified from CB to CE. So, this I can write CE by CB into the vector CB, which takes care of the magnification by a factor CE by CB, and to represent the change in orientation between the vector CB and CE through an angle alpha, I have to multiply it by e to the power I alpha. Now, vector AB I can write in terms of vector AD exactly the same way. I write the magnitude has been magnified by AB by AD and the vector AD, and the vector AB is at an angle alpha in the counterclockwise direction from the vector AD. So, I multiply this by e to the power I alpha plus this term. So, I have the vector y as AB by AD into vector AD e to the power I alpha plus CE by CB into vector CB e to the power I alpha. Now, because these two triangles ABD and BCE are similar triangles, it is easy to see that ratio AB by AD is same as CE by BC. So, CE by CB is same as AB by AD due to the similarity of the triangles ABD and BCE. So, I can take this ratio AB by AD and this factor e to the power I alpha common. Consequently, what we get is that vector y is AB by AD into e to the power I alpha, which we take common, and we get AD plus CB, which is same as O2A, and AD plus O2A is nothing but our vector x. So, AB by AD into e to the power I alpha into the vector x. So, we see that the position of these two vectors, that is the point E and the point D, is given by y and x, and they are related through this equation. Y is changing with time, x is changing with time, but the link lengths AB, AD and the angle alpha of that triangle are not changing with time. So, this factor is a constant independent of time. So, the movement of the point dy, I can write AB by AD into e to the power I alpha into dx, where dx represents the movement of the vector x and dy represents the movement of the vector y. So, we see that movements of y and x are very similar, but for this factor. That means, the movement is magnified by a factor AB by AD, which is the scale of reproduction which I wrote earlier L by L, and there is a rotation through an angle alpha in the counterclockwise sense. So, sigma, that is the change in orientation of the reproduction, is equal to alpha. To make it clear, let me go back to the previous slide, that AB by AD, that is the factor of reproduction, that is this length by this length, that is this letter h is reproduced to a bigger scale, namely by the factor AB by AD. Not only that, this vertical side, which is vertical like this, has been oriented through an angle sigma, and we have already shown that sigma is nothing but the angle alpha. So, this is the copying mechanism, that any arbitrary figure drawn by the point B or followed by the point D can be reproduced at the point E at a different size and different orientation. Let me now summarize what we have learned today. We have shown how we carry out the displacement analysis of planar linkages by analytical methods. In the analytical method, we represent all the kinematic dimensions like link lengths, offsets or slider displacements by planar vectors. And using the closed loop that exists in the mechanism, we generate a loop closure equation, and then by solving this loop closure equation, we can finish the kinematic or displacement analysis of planar linkages. We have given the example of a simple 4R linkage and also a 6-link mechanism where you have more than one closed loop. Finally, we have shown an example that shows the power of this vector representation for link lengths to analyze the copying mechanism or the plagiograph.